All right. Get these lights turned on. And we'll keep going. So, kind of pick up where we left off last week. We're still just going to be doing review statistics, probability. So we'll do some work in Stata here today. I'll mention some more things just to kind of try to help solidify. If you still don't have it working, hopefully you've kind of come talk to me. I haven't had many people show up in my office hours. That's a really good time to kind of get help with some personalized kind of Stata work. So tomorrow, I'll put up an announcement after class. I'll basically be in my office most of the day tomorrow from like 8:30 to like 3:30. So there's a time that it's well for you to stop by. I'm in there. My door's closed. I'm just working knock. I'll open it up. Be more than happy to kind of help you. But we got a lot of those issues. People that stayed after last class. We got everyone that stayed after. I think we got all the issues resolved. A lot of the times it's just you might have selected something wrong early on in the process. And we just have to kind of go redo everything. So we'll do a little bit of work in Stata here today, but kind of starting out before we jump into material, I want to mention a couple things. So we've got the skeleton slides for the week. That's what we'll be kind of going through. A bunch of different data files we might start using. We're going to use this Excel file, group data covariance, just to kind of have a nice place for me to put a bunch of numbers that we're going to kind of work through how we calculate covariances when we have probabilities associated with saying certain values, or we have grouped data. We're going to use the Z and T tables later on this week, maybe even hopefully we'll start looking at them today. I might work a little bit quick. Once again, this should be review. I know I'm just in some blank spaces, so I'm trying to go a little bit slower through it here. And I also put up sample questions. So after Thursday's class, I'm anticipating we're going to have that first quiz, right? So that'll be due before we meet in class the following Tuesday. So I'd start looking at these sample questions. Probably the first half are going to look like the stuff that we covered last week, and then they've been up there, so you kind of could have started looking at them early. I would start looking at them, kind of getting prepared for that quiz. It'll be anything we covered here in the first 2 weeks. I also put up the first problem set. So once again, the first half of this was stuff that we did last Thursday's class. Okay, the rest of it will be stuff that we pretty much do today and a little bit on Thursday. So I've gotten the current due date set to be next Thursday. Right, so you'll have really more than a week to work on it. Now, obviously, you probably couldn't finish it today based on what we covered in class. But if you get kind of an early start on it, that first half should look like stuff that we did last class. Pretty basic, kind of summarizing the data, finding the mean, standard deviation, maybe creating a histogram or a scatter plot. We'll review that again here today. But I would start working on that problem set so that the last half of it, after we cover on Thursday, you've got about a week to get on and get that completed. Okay. So we'll dive into it here. Okay. So we talked a little bit last class. We have two random variables. We said we can calculate the covariance. So basically, it's going to be, is the X variable above or below the mean, multiplied by how far away the Y variable is above or below the mean. We then do that for every single observation, right? That was our summation sign, the first point in our data set to the last. We add them all up. If it's then positive, it tells us that these two variables tended to be on the same side of the mean, or they have a positive correlation. If we add these all up and it's negative, we said that means that they tend to be on different sides of the mean, or that when one is low, the other is high, or they have a negative correlation. We also then said, well, what the hell are the units in these covariances? Like they can't really compare across different variables because they're all weird, goofy student points, or I think I had some other examples we could do, like, I don't know, GDP, if we're concerned like the GDP and education, dollar years of college or something, some weird units. But we can scale it by dividing by the standard deviation of each variable. And what that should do is it gets rid of our units. We can now compare across different variables, but it also is going to scale that correlation, or sorry, scale that covariance to a correlation that's between 1 and -1. 1 representing the strongest positive relationship, -1 the strongest negative. Okay. So we said we can kind of look at this like with a scatter plot. We're just creating a scatter plot with the data, and when we jump back into Stata, I'll remind you how you do this. It's a pretty basic command, and there's an easy way to do it kind of from the interface. If I had to draw a line that kind of best fit this data between class size and math scores, I'll probably draw a line that's upward sloping, right? So it has a positive slope that's telling us that it has like a positive covariance or a positive correlation coefficient. Okay. How can we actually calculate this? Okay, so I've got this grouped data covariance example. And I had population of different cities and their violent crime rate, okay, per 100,000 people. So we're already scaling this by people. I then kind of had this idea of like, okay, and here let's zoom in a little bit because this is kind of small. 150 going to be too large? Nah, that's all right. So I've got the data over here. Now, we won't be doing a lot of work in Excel. We're going to primarily be using Stata. But if I treated this data as kind of continuous, how would I find the mean of these two different variables? Simply do what? If you had to tell me in words. If you wanted to find the average or the mean of a set of numbers, what do? Add them up, divide by the number of values you have. Okay? So that's all that we're going to do here. It's just we've got a nice easy built-in function in Excel, just like we had a nice easy built-in function in Stata that'll do that for us. It saves us a lot of time kind of doing this work by hand. Okay? So I've got kind of the average here of that violent crime variable. I then looked at, okay, does medical marijuana mean? So this was just a variable, and we'll start dealing with some of these variables that we should call them like indicator variables, right? Which is just a 1 or a 0 if, I guess it's not cities, I had states here. 1 if medical marijuana was legalized, 0 if it wasn't. Okay. So I've got this kind of indicator variable. It was only ever 1 and 0. Well, if I find the average of this variable, what is that actually telling me? 0.42. Well, if I'm adding all these values up, every time there's a 0, nothing gets added in. So what would the numerator of my mean tell me? The number of states that have legalized medical marijuana. What is the denominator? All the states. So if I take the number of states that have it legalized over the total number of states, that's going to be the proportion of states that have it legalized. If I wanted to convert that into a percentage, what would that be? 42. So 42% of the states here have medical marijuana legalized in, I forget what year this data was from. It's probably a little bit older. Yeah, 2014. Okay. So I can find the means of these two variables, and I could find the standard deviations relatively quickly, right? So once again, just like I actually kind of, oh, sorry, that's not the one I want. I did the group data here. If I wanted to find the standard deviation, there's a built-in standard deviation population function. We could do that. We're not going to use it for the sake of this example, but we have that built-in function in Stata where we could calculate it as well. Now, if I don't have this nice continuous data, right, where I have like every individual in my economy, it's grouped by states, right? Or in fact, not only each individual state, if I were to just give you this table here, this is telling you if you were to select a state at random, the probability that it has medical marijuana legalized and has an above average violent crime rate. Now, I chose an easy number here. It's not technically the average, right? The average is 346. I chose, well, these should be the same value here. So I kind of chose 400 and 300. You could think of this as above or below the mean. I made this a little bit easier, right? I said the proportion of states that have medical marijuana legalized, and let's say for those that have an above average mean, the average violent crime rate was 400. So I'm giving you that value instead of the actual mean, okay? So 22% of the states had that combinations of things being true. Now they didn't have medical marijuana legalized and they had a below average mean. The average was 300. So the number of states that kind of are in this category where the average violent crime rate is 300 and they didn't have medical marijuana legalized is about 34%. Now these totals, if I'm just adding kind of down the columns here, what would this proportion represent? The number of states that what? If I'm taking the number of states that have above average mean or 400 violent crime rate, they have medical marijuana legalized, and I'm adding to that the states that have above the average mean or 400 violent crime rate, but don't have it legalized. That's every state that has a high violent crime rate, essentially. So kind of these totals represent the probability of this event, of having the average violent crime rate or being in that above average kind of category of 400 violent crimes. And then about 54% of the states had that average kind of violent crime rate of 300. Okay. So that's how I'm going to read. This is a joint probability table. Hopefully you saw these in 370. Okay. So if I have group data, how am I going to find that covariance or that correlation coefficient? Okay. Well, if I wanted to find kind of my group data's mean, so we'll do just adding in some stuff here, not violent crime. Now I'm going to kind of abbreviate. What would I do? Okay. What's the violent crime mean here? I would look at, okay, what's the probability that the state, if I selected it at random, had a violent crime rate of 400, right, or belong to this category here, it would be 0.46. So we do the probability that we see a state have that violent crime rate of 400 would be about 0.46. Now, what's the only other outcome we have in this easy joint probability table? That they would have it be in this below mean category. So probability there was 0.54 times what's the violent crime rate of people in that category? We said it was 300. Kind of just making it two values. You know, we could do more than two. It just makes the math a lot more, a lot more moving parts. So I can calculate means, and I get, sure enough, that violent crime rate is about the mean if I had the actual continuous data. It'll be a little bit off because I changed the numbers to be kind of nice round numbers. But it's essentially this going to produce us the same value. Now, if I was doing the standard deviation, it's a little bit trickier. I'm going to take every possible value, 400 and 300 here. I'm going to subtract the mean and then square it, right? And then I left something out here. What did I leave out? If I'm calculating this as group data, here was the outcome of seeing that they had 400 belong to that category where 400 was the violent crime rate. But the probability, I didn't factor in at all, right? So what I should do, unlike a regular kind of standard deviation, where if I only had two values, it'd be easy to find each deviation from the mean squared, then add them up. What I should be doing here is taking each deviation from the mean squared and multiplying it by the probability I see that value. Or if I don't want to use cell references here, I could just grab that value like this. Now, I also need to look at the other outcome of seeing if I selected a state at random having 300 as the violent crime rate, I need to make sure that I multiply that by the probability I saw 300 as well. And hopefully you saw me quickly edit. I had a typo. I had too many zeros here. It was 300, not 3,000. So I wanted to kind of set this up so I could show you what you typically would think of as calculating the standard deviation. When you have group data from this joint probability table, we need to factor in those probabilities, okay? So you'll see a problem like this on the practice problems. You might see one like this on the quiz, okay? There I've got my kind of violent crime standard deviation. Same kind of thing down here. I added in the probabilities down here, so I didn't leave them out since we've already talked about it. But once again, I use cell references. You could have just put in 0.42 and 0.58. Okay. Excuse me. Any questions on that before we keep moving here? So it gets a little bit trickier. If I want to look at the covariance, I have this really long kind of line of text here. Now, I've got a bunch of stuff in here that I'm not going to make you reproduce. We're going to use this and I'm going to show you how we do this. Okay. So I know that it's going to be on two different screens, but I'm going to reference these numbers, so we'll want to have them, okay? So if I was calculating the covariance between these two variables, I'm thinking about now not breaking this down kind of each kind of category. I need to use all of those top four cells for the joint probability because there's four different combinations of having medical marijuana legalized and having this violent crime rate of 400 or 300. When I was just looking at one variable, right? I was looking at one variable. Now I'm looking at two. So the first thing I'll do is say, for this category, if they had this medical marijuana being equal to 1, so that was the value of my Y variable, if you want to think about it that way, what was that deviation from the mean? Well, we had the mean calculated. Now, let's see if I can get, there we go. So we had the mean calculated was 0.42. So what we're going to do is first say, okay, if I think about these possible, and I'm calling this Y, deviations from the mean for each of my variables. The very first one was I saw 1, right? They had medical marijuana legalized minus the mean of that medical marijuana variable. And then that second variable, we had, it was in the 400 violent crime category. So we were going to take the value of 400 minus what was the mean of our violent crime variable. I think here, not using the continuous one to kind of keep this kind of nice and easy, we'll use this round number of 346, right? That was our mean. So I'll put that 346 in there. What do I then need to do? Go to one of the other groups, left something out. Looking at a joint probability table. So what's the likelihood I see these deviations? I need to multiply it by the probability that I have this above kind of mean this 400 violent crime rate, and I have medical marijuana legalized. So I need to multiply it by 0.22. And I'm going to add to that. What's the next possible combination of these two variables? Medical marijuana is 0. So now the deviation of that value from the mean multiplied by, well, I'm still in the above kind of mean column or this violent crime rate of 400. So I'll use the violent crime rate of 400. It's deviation from the mean. What's the probability I see this combination of the X and Y variable? So medical marijuana is not legalized and they have the 400 violent crime rate. That probability is, okay. Yeah, 0.24. 0.34. No, right? So they don't have medical marijuana legalized and they have this high 400 violent crime rate. That probability is 0.24. Yep. So the 0.34, we think about what's the next combination of this X and Y value. So we can do it in either order. Since you mentioned it, I'll do this one first, but we still have two of these cells remaining, right? Two different combinations of this X and Y variable. So here, they don't have medical marijuana legalized, but they have this low violent crime rate. So the value of the medical marijuana is 0 minus the mean, multiplied by now that value of 300 minus the mean of the violent crime rate variable. And then what's the likelihood we see that combination of the X and Y variable? 0.34. Right? So we then multiply it by the probability we saw that combination of the X and Y variable. Okay. Now we have one left. It's going to be medical marijuana is 1. You have the low violent crime rate of 300. So 1 minus the mean of that medical marijuana variable, 300 minus the mean of that. And then what's the likelihood we see that? 0.2. I'm looking at that joint probability table, kind of going like this. This should give me my covariance. Okay. So if we're doing that, put this into our calculator, or did here, I kind of have all those values, and I did 1 minus there. It's kind of a way to play around with kind of these different probabilities. So you know, this isn't going to match up exactly with what I wrote down because I was doing some things to kind of do it a little bit quicker by hand. But basically, it should reproduce to us that covariance. Okay, so I would, if I'm doing this by hand, don't worry about the Excel file because you're not going to likely be doing it in Excel when you're taking the quiz. You're probably going to do this by hand. I would kind of do it this way. There's going to be 4 different combinations of the X and Y variables. You kind of take the deviations of each of those values from the mean for those variables and then multiply by the probability you saw that combination. Now, if we do this, all right, I've got covariance here. What did we also have? We had the covariances. So if I want to find my correlation coefficient, what's the next step? I'll take my covariance and what did I say? We'll divide it by, started out with the slides. We just divide it by the standard deviation of each of those variables. So you'll first need to calculate the standard deviations of those variables. That was a little bit easier because it was just one variable, right? We're just looking at the deviation of 2 possible outcomes, for each of those variables, and then multiplying them by the probability we saw those outcomes. Once I have the standard deviations, I can find my covariance. Once I find my covariance, simply divide it by those standard deviations, and that should give you my correlation coefficient. On the quiz, I'm likely to simply just ask you to find the covariance, not do all of those steps because that would take a lot longer and there's a certain time limit on the quiz. So really the calculation of the covariance is going to want to be what you focus on, which is why I want to make sure I went through it here in class today if we're dealing with one of these joint probability tables. Okay. We had the notation that we looked at last week, but it's going to be a little bit different. Any questions? Yeah.
So are we going to be a situation where like the 0 and 1 aspect, that's just like
I could give you different values. I had it set up as a 1, 0, 1 because it's a little bit of a unique, kind of different able to see. Might even be a little bit easier for you to think about if you had 2 kind of normal variables that one wasn't 0, 1, but it's really the same steps, right? Instead of 1 and 0, it would be 200 and 750, or whatever the 2 values would be for those groups, those categories.
So did you say the covariance divided by the standard deviation is the correlation?
Yep. So we're looking at, we said, if you want the formula, we take that covariance and we divide it by the standard deviation of each, or the product of the standard deviation of the 2 variables we were looking at the covariance for. That should give us this correlation that lives between net 1 and -1. In fact, if we do the calculation and we find something that's not between 1 and -1, we know we made a mistake somewhere, right? So like, let's say I don't know, forgot a probability. Oh, I made a mistake, right? I got a correlation coefficient above 1. I know I did something wrong, right? Didn't, right, in the equation, but if I had forgotten the probabilities, that's what would happen. Okay. Questions? Yeah.
I was gonna say, on our like weekly or bi-weekly assignments,
Mhm.
are we ever going to have to like, actually type out the math, or do you?
So-
Like,
So I think I said this, but it's been a while, probably from day one. So the quizzes, right? All of that, a lot of that work, that's primarily gonna be done by hand, right? You're gonna be answering it's on Canvas, you're gonna have to input your answers. I guess technically, probably a way you could use Stata if you turn every question into a data set, but I'm not expecting you to do that, and it would probably take way too much time. So when we go through things like this in class, that's gonna look more like what you see on the quizzes and probably the exams, right? With the exception of on the exams, I'll give you some output from Stata and then ask you questions about it, which is why those problem sets, which are just, all I'm expecting you to do on those problem sets is to use Stata. So those problem sets you shouldn't have to be doing. Now, you might have to like so let's say Stata didn't have the capability. It does, but let's say it didn't tell you the correlation coefficient, but it would tell you the covariance and the standard deviations. Those problem sets, you would calculate those statistics you need using Stata, and then there might be like a small calculation to get. Now, most often that's not going to be the case. When we get further down the road, we'll deal with like we'll deal with coefficients, and the coefficient tells you the change of 1 unit. I might ask you, what if it increased by 200 units? Well, you got to get the coefficient using Stata, and then you might have to just multiply it by 200 might be part of what you have to do. But you can do that in your Stata code as kind of like a green line. Remember, I said you had text, so we just do kind of a backslash, but it's not going to be near as like involved as something like this that you would have in those problem sets. Is that what you're asking? Yep. Okay. Any other questions on this joint probability before we switch gears here a little bit? Yeah.
See the criminals under 5.
Slides. Now I'm going to switch to those anyways. Okay. So we had our scatter plot. I'll do this in Excel. We'll now kind of start thinking about conditional means, right? And kind of pushing that even further into Stata eventually. So if I have a variable, right, it might take on a different distribution. So we talked a little bit about touch on distributions last class. I kind of showed you the hist command in Stata. We can kind of see, oh, most of the values for this variable are kind of centered around this, and then it kind of trickles off. We might have very different distributions if we condition on something, right? So I think about this, like I've got different groups. If I'm looking at average test scores, so that's my kind of Y variable here. And I know it gets kind of weird. A lot of times we'll like use Y to represent the variable as opposed to X. I know that's more common in other math classes, but typically the variable we're thinking about, we usually kind of use Y. So I want to know the expected value or the average essentially math score for, I'm going to condition here on if they had 16 years of education. So I try to kind of create these groups, college degree versus only a high school degree. Now, what would you expect the average of someone with a high school degree to be compared to someone with a college degree? It's likely going to be low. So we know there's probably going to be differences in means. So I actually had some data and I calculated kind of not just like earnings, but I calculated the math score here, right? And sure enough, it's a little bit lower, right? Now, if I was to draw out the whole distribution, I don't want just the average. I want the probability of seeing all the different possible math scores. So we know we can find these kind of conditional means, but we can also find conditional distributions, right? So what's the real value, I guess, kind of completing this example? If I can find these conditional means, I could do things like, okay, what's the value of a college education? Well, here, it's not in terms of money, but like, what's the difference in the expectation of performance on this math score for someone that has a college degree versus not? I would just look at the difference between those conditional means. So when we say conditional, when I write this like vertical line, it's saying, what's the expected value of this Y variable math score given or conditional on that this other variable is equal to a specific value, okay? So that's gonna change wildly, right? Like what's the expected, what's the expected debt of someone who has income equal to 20,000 a year versus someone who has income equal to 80,000? So, you would expect the debt of the first person probably significantly higher, but maybe not, right? Maybe they don't live outside of their means as much, and maybe you actually see debt. We don't know the answer to all these questions, but we know that there's going to be a difference in how those people act, right? In terms of what their debt's going to look like. So condition, right? It's essentially you read this vertical line as given this is true. What is the expected or the average math score given this variable X, which was represented here? I had parental education, but you can think about his own education, is equal to 16. So one thing we can also talk about will pop up here and there throughout the semester. If the expected value of your variable, whatever you've conditioned on, is the exact same as the unconditional mean. So remember mu of y, that represented just the overall mean of this variable y. If by conditioning on something else, the average of that y variable is still whatever it was before you condition on it, did conditioning on that event matter at all? No, it gave me the exact same. So we would say those are independent events, right? So I might use the math score when I say, okay, what's the expected value of someone's math score? I don't know, given that their hair color is blonde, right? Likely, there's gonna be no correlation, right? It's gonna be exactly the same as whatever the mean was if I didn't condition on that, right? At least in terms of what I know, there's no evidence supporting that hair color impacts intellectual intelligence at all.
What is the significance of the 350 numbers? Like, what does that mean?
So when we say the expected value, that's another way of saying the average. If I were to choose kind of a variable at random, on average, I would get the average value. So the expected value of this math score conditioned on.
Oh, so that's just the score, the math.
This is just the average score after I've conditioned on this other variable being equal to a specific value. Okay. Is that?
Yeah.
Okay. So if by conditioning on that, I found the exact same value as what the mean was by not conditioning on anything, we would say these are independent events, okay? If they're independent events, there's no relationship. What should the covariance and correlation coefficient be? 0. So independent events should have this correlation or correlation coefficient of 0, right? They don't depend on each other at all. They're not related. So I've got this one where I'm going to draw this out for you. Let's say I thought of a different thing, looking at, I don't know, potential future starting salary for someone leaving Indiana University, right? So I've got kind of my probability that I see this variable y take on different values, and I'm thinking about the variable I'm interested in, y. I forgot I had to press 2 buttons in this classroom. Usually I just have to switch to the dot cam, and this one I have to like hit what I show you guys on the projector. So if I do that, I'm still getting used to it here. I usually just have to hit the 1 button. I have to do that on my earlier classes too. So I'm like already in that kind of routine. My motor skills are already in that routine. So here's my starting salary, right? Here's the probability I see those different values. So maybe I look at something like this, and here's the starting salary for a student who doesn't take 371. They're going to be all over the place, right? You all are not going to get the exact same jobs, and some of you will get lower paying jobs and some of you will get higher paying jobs, right? There will be, most of you get about whatever the college is putting out as the average starting salary. The highest probability is going to be associated with the values right around that mean, right? So we could even have an example, right? In this case, where I've got, here's my kind of mean of kind of conditioning on that this person graduated with an econ degree and didn't take a applied econometrics course, right? Taking this applied econometrics course, if I do my job right, or you at all can take in any of this information, should make you a lot more marketable. First of all, there's a lot of econ majors who don't have like near any kind of background in math and statistics, right? It's just the way the world works. You're just not as marketable. I don't make the rules, right? That just is what it is. You're not going to be, and I say you're not as marketable. You're not going to be as marketable for higher paying jobs. You might find value, right? Your marginal benefit might come from like intrinsic love of whatever you're doing. But if we're just talking about starting salary, it's likely that these really low starting salary values, it's less likely that if you have 371, you're going to have that starting salary, And what ends up being true is you're more likely, if you take 371, you're gonna have a higher probability of getting a job with these higher starting salaries, right? So conditioning on this one thing that you took a 371 course or didn't, right, or equivalent, the probability, right, not only would we see a higher mean for that group, the whole distribution is likely going to shift. So when we look at these conditional statements, it's going to change the distribution of the same variable, right? Because conditioning on this thing matters. These are not independent events, right? Your starting salary is going to be tied to the types of courses that you took prior to applying for that job, okay? Is that any questions on that idea? A little selfish plug and promotion for this class, but like I said, having some, and like, even if we're not masters at the end of the semester, having some experience working with a data management program, I'm telling you, it sets you apart from so many other, like, if you're competing with the Kelly students, it's a little bit different of a story, right? They're gonna have similar kind of skill sets, which is maybe why you wanna have something like this, because now you can compete better with them. But for econ majors that don't have these kind of experiences or skills, you know, it's tough, right? It's tough out. All right. Any questions on that? So just kind of getting at this idea that the entire distribution could change when we make these conditional statements, okay? So we're now going to move towards, we know that variables have their own distributions, and we know that conditioning on different things might change those distributions. But ultimately, we want to know, if I chose someone at random who had 371, what's the probability that they have a starting salary, say, over, I don't know, $60,000, right? Well, we can find these probabilities by converting these variables essentially into what we're going to call, talking about the normal distribution, and eventually the standard normal distribution. So all a normal distribution is, we'll kind of go through this kind of quick, is a symmetric distribution. Touched on this a little bit last class. If the mean is the same as the median, right, it means that we kind of have like mirror images of this distribution. It's going to be symmetric. If I folded it in half around that mean, which is going to be the same as the median, it would exactly match itself, right? So seeing a value that's, say, 30 below the mean has the same probability as seeing something 30 above the mean, right? Now, these normal distributions, we're not at the standard normal yet, are still going to be defined. They're all symmetric, but if I have a higher mean, I could have two variables that are normally distributed. So for example, IQ is a pretty good, has a good normal distribution to it. If I were to use some other aptitude test, like, what's another one, that the ACT or the SAT, they're normally distributed as well, but their point systems are way different. So like the SAT is going to have a much higher mean than, say, the ACT. So they're still defined by their mean. That's going to shift the distribution along the x-axis, right? Something with higher means is going to be shifted to the right, right? Now they're all symmetric, right? All of them have the same, their mean is the same as their median is the same, their mean is the same as their median is the same as their mode, but that mean would shift where that distribution, that normal distribution is. Now, even if it's symmetric, right? The mean is the same as the median. It's like exactly folds on top of itself. What else also matters is the variance. So if I have a normally distributed variable, right? And let's say I start out with a variance of 5, okay? If I have more variation in the data, what's going to happen to the probability I see values that are further from that mean? Is it going to go up or down? So if the data varies more, is seeing values further from the mean going to be more or less likely?
More likely.
More likely. So if my y-axis, when we had plotted here, was representing probabilities, what's going to happen to the values out here? This line is going to be higher. Now, what's going to happen to the probability associated with seeing values close to the mean? If there's more spread out, if it's more likely I see values further from the mean, well, that has to come from somewhere. That means it's less likely I see values that are around the mean. So when I'm looking at things with higher variances, more spread out, I still have a normal distribution. It's still symmetric, but it's getting flatter. So the mean will shift our normal distribution to the left or right, depending on if it's higher or lower. And the variance, the higher the variance, they're kind of more squished down, if you want to think about it that way, or like the flatter this distribution will get. If I have a very low variance, what's going to happen? Well, if we work in reverse, going for lower variance, it's going to make it more peaked. right? Those probabilities around that mean value become very, very high. Okay. Any questions on this idea so far? So we're just kind of touching on these traits that define distributions. So I had some old data, I had height data, right? We can kind of think about male and female height, both normally distributed. Now, I'm not looking at all height here, right? I'm looking at conditional distributions. Here is every height conditioning on the individual identified as male. Here's the conditional height that or individuals identified as female, right? So what do we notice? Male height is going to have a higher mean, right? That distribution is shifted to the right a little bit. Which of these male or female height has more variability? Male, right? We said the higher the variance, the kind of more squished or the more spread out that distribution is going to be. Now, it's kind of hard to, I usually don't like to use the word of like spread out because visually it's kind of hard to see that it's more spread out maybe. But if you think about it, that it's like squished down more, right? That represents that it has more variability. Okay. Which is true about almost every, you look at like gender, condition on gender, usually male distributions tend to just have more variability. I think there's some hormonal reason about testosterone has a wider range of variabilities like in every single physical thing, but I'm also not like a biologist or anything like that, but I knew a little, I've read a little bit about it. So now that we have these distributions, we want to think about what's the area under any distribution, or what's the area under the curve? Well, if this is the probabilities associated with seeing every single possible value, if I add up the probability of every single possible outcome, what should they always add up to? 1 or 100%, right? So I've got the area under my curve will always be 1. What'll end up being true, and we'll kind of prove this to ourselves, and this eventually leads us to this standard normal distribution. But if I'm looking at a normally distributed variable, if I go 1 standard deviation to the left, and I take that value, and I go 1 standard deviation to the right, I take that value, the probability if I was to select one person at random, that their height would be in between 1 standard deviation above and below the mean will always be what, like 68.3%? It'll always be the case. And we can prove this to ourselves once we get to the Z tables, right? But for now, you can take me at my word, right? So we kind of write this. If I have this random variable X, if I take 1 observation at random, the probability it's 1 standard deviation below, somewhere between that and 1 standard deviation above, it'll always be that same probability of 0.683 or 68.3%, okay? All right, so visually, we're kind of thinking about the area under the curve, but between these two values. And we can come up with these two values. We looked at it already and stated. I can calculate a mean. I can calculate a standard deviation. I could figure out what those two cutoff values are. And that would give me that 68% probability. Now, if I go 2 standard deviations to the left and 2 standard deviations to the right, what's going to happen to that probability? The probability I'm within 1 standard deviation above and below is 0.68. If I go 2 standard deviations above and below, what's the area under the curve going to be? Larger. If I expand this, have more area, that probability is going to be higher. And that kind of makes sense. If I tell you if you chose someone at random, probability they make between 50 and 60,000, well, that's going to be lower than the probability they make between 50 and or 40 and 70. Right? You're just giving me a much wider range of possible values. It's definitely going to be more likely that they make somewhere, in that range. So that's all we're doing here. As we go further standard deviations away from the mean to kind of create these boundaries, we're always going to be getting larger and larger probabilities. So at 2 standard deviations, we went from 68% to there being a 95% chance if I chose someone at random, they're within 2 standard deviations above or below that mean. Okay. So this is going to be true about any symmetric or any normal distribution. Sorry, any normal distribution that is symmetric, right? That's one of its characteristics. And then I go to 3, it's going to be even higher, right? You'll notice here, the rate at which it increases starts to go down, right? We went from 68 to 95 to 99. At this point, we're getting pretty close to that probability of 1. In fact, you guys aren't like kind of a business school, but you've heard this probably. Have you ever heard of 6 sigma? They kind of say this with like financial companies. Well, what is this? So this is 3 sigma, and we're almost at a probability of 1. 6 sigma is kind of this idea that like, if I go 6 standard deviations above and below, what's the probability I see something in that range? Well, we're already at 99.7 at 3. So at 6, we're going to be 99.99999%, right? That's kind of, it's coming from this idea, right? Sigma is our standard deviation. Okay. All right, so because these normal distributions are defined by their mean and variance, we'll start writing them out. Here's this random variable x. It's normally distributed. You might think about things, we won't use it in this class a lot, but like there are different distributions like uniform distributions. We're primarily only gonna be focusing on normal, kind of standard normal distributions. But this variable is distributed normally. That's kind of what n stands for. And then what defines the normal distribution? Well, what does its mean? What is its variance? Right? That tells us about where we would plot that distribution on a graph. Okay. All right. So we have a special case of the normal distribution, which is the standard normal distribution, which is it has a mean of 0 and a variance of 1. So we talked about this a little bit last class. How did I get the mean to be 0 and the variance of 1? Do you remember what we did on Thursday? It's kind of already up here, the word. I said I took a variable and I standardized it, right? By doing what? I subtracted the mean and I divided by the standard deviation. So we can take any normally distributed variable, we can take any variable and we can standardize it. How do we do that? We subtract the mean, divide by that standard deviation. That should give us a new variable, that standardized variable, which should be standard normally distributed with a mean of 0 and a variance of 1. Okay. And then we can use this along with the z-tables to start to find probabilities of seeing different values. Okay. So building up, we're kind of getting all these tools, hopefully to be able to start to actually work on some problems here. Oh, did I repeat my slide on accident? Yes. So we have this normal distribution that has a mean of 0, variance of 1. We can now start to think about this standard normal distribution. The values essentially will represent how many standard deviations away from the mean that specific value for x is, right? So if I think about my standard normal distribution, right? If I'm looking at a z-score, once I've standardized this variable, if the new standardized variable is a value of -2, what that's representing is whatever the original value of that variable was, it was 2 standard deviations below the mean. Okay. And then if I think about a z-score of 1, right, after I've subtracted the mean, if I have a z-score from this standardized variable of 1, that's telling me that that value was 1 standard deviation above the mean. So z-scores have a really nice interpretation for us, right? It's the number of standard deviations away that value was from the mean. Okay. And then the negative sign tells if it's below, positive if it's above. So how do we calculate these z-scores? I kind of already alluded to it last class a little bit in that state example, but we take the value for x for that observation, we subtract the mean, we then divide by the standard deviation, right? So we're going to want to do this a lot, right? So kind of burn this into your memory here. If you want to standardize a variable or you want to convert a variable into a z-score, you subtract the mean, divide by the standard deviation. So here I've got, kind of back this out for us a little bit to kind of give a little bit of insight as to why that interpretation is what it is. So let's think about where that z-score equation comes from and why we can interpret that. So let's say I had some value, this x variable. If I were to say, okay, if I take this value, and I want to say how many standard deviations, or I want to say this is, well, oh, I got to switch it over. Thank you. That'd be bad about this here. All right, so we'll start over. All right. So if I took something and let's say it was 2 standard deviations above the mean, right? So that's what my x value is equal to, right? It is 2 standard deviations above the mean, okay? If I rearrange this equation a little bit, right? So let's say I subtracted kind of from both sides this mean here, be left with this. And then if I divide by standard deviation, notice what am I left with? I'm left with 2. That thing I told you was calculating the z-score. It would be that it's 2 standard deviations above the mean. In fact, I could keep this more general. Now I have to come up with a different value. If this is z, right? I use the same process. I just kind of rearrange this equation. And I get, okay, that z-score, which represents the number of standard deviations above or below the mean, that's the equation that I would have to solve for. So that's where that comes from. Okay? So we're going to use this to standardize variables so that we can kind of know how many standard deviations away above or below the mean they are, so that we can then use those z-tables and find the probability that they were above or below the mean. So I'm probably jumping the gun a little bit here. Since we're already here, we're going to be doing something like this. Okay. So let's say I have this random variable x. It's normally distributed. And I don't know, maybe here's the mean. And just to kind of put some values to this, 1,000. This is like the starting salary. I want to know what's the probability that if I was to select someone at random, I see them make $60,000 or anything below that, right? So I want to find the area of the kind of, or this probability that I see a starting salary of 60,000 or below. Well, those z tables is for a standard normal distribution. Doesn't matter if it's normally distributed. Okay? So what I'm going to do is I'm going to convert that variable into my standard normal distribution by creating for every single possible x value, I'm going to turn them into z-scores. Because those z-scores that when I subtract the mean divided by the standard, that's what I know is standard normally distributed. So if I take this value of 60,000, I subtract the mean, and I don't know, let's say the standard deviation here was, oh, what do I want to make this nice and easy? 10,000, right? I divide by my standard deviation, I get a z-score of 1, which sure enough, right, I was 1 standard deviation above the mean. I can then go to those z-tables and I can find that z value of 1. So I have to first take this variable that's normally distributed, convert it into a z-score, which I then know are standard normally distributed. And then using that z-table, or eventually in Stata, we'll use like these kind of basically pre-saved z-tables that live in the background. We can then find that probability, right? So the area under this curve, remember, between two values represents a probability. Before we were going like 1 standard deviation above and below. Here I'm just saying, what's the probability it's 1 standard deviation above or anything less than that, right? So I'm just still having an interval, right? It's just wider, okay? Is this hopefully looking a little bit familiar? So a couple head nods, okay? So we've got this normal distribution. We kind of already talked about its interpretation, the sign. We can standardize any variable that we want by subtracting the mean, dividing by the standard deviation. Hopefully, if we do so, we'll end up, after we standardize it, it has this mean of 0, standard deviation or variance of 1. Now we can use the standard normal distribution. And this is where I kind of jumped the gun a little bit last class, and I showed you already how we standardize a variable in Stata. And we'll revisit this when we kind of jump back into it. Okay. So we did this already in the last class, so I'm going to skip ahead a little bit so we can at least look at the z-tables today. Well, like I said, we'll revisit that Stata do file either at kind of very end of class today or kind of beginning of class tomorrow. Or tomorrow, Thursday. It's not Thursday. I'm talking too quick. So if I had this variable of human height, so this is a histogram that actually came from Stata, right? I think it was an older version. The newer versions, they've started making the graphs look a little bit nicer. But here I can kind of see, if I had to guess, like about what is the average human height here? Looks like it's at about 70. I think this was inches, right? So about what? 5'10", and then I might have conditioned on making this male height. I can't remember. But I've got what looks to be a pretty symmetric distribution. It's pretty close to a normal distribution. Okay? So I can look at other things. I think I grabbed, this was like, I saw this pop up somewhere on social media, and it was like, I think CrossFit data, and looking at like the performance. Like, there's a lot of human performance things that follow pretty close to a nice normal distribution here, right? There's something weird going on with the one, a little bit of a blip there, but pretty close to a normal distribution. So why are we going to use these z-scores? We already kind of set this up. We want to find the probability we're in between two specific values. Okay. So we can use a cumulative distribution, but it's going to be a little more complicated. So we're going to look at these standard normal tables that someone's already kind of built for us. So let's say we start out with the initial example. I convert my variable into a z-score. I get a z-score of negative 1.29. Okay. So that was originally some height value. So maybe I had the human height value here. And I don't know, maybe it was like 65. I turned that into how many standard deviations below the mean it was, and I get negative 1.29. It was 1.29 z value. That means it was 1.29 standard deviations below the mean. But what's the probability when I chose someone at random, I saw a height that was that low, or anything lower than, right? So we're gonna use these kind of cumulative distribution, right? The probably you see this value or anything below it, and that's what the Z table is gonna give us. It's gonna give us this cumulative probability. So when you look up negative 1.29, the Z table we're about to look at will always tell you the probability of seeing that Z value or anything below it or anything to the left. If you want to think about it that way in the distribution. Okay. So what does the Z table look like? Right? Probably hard to see for some of you in here. It's kind of smaller. I've got a PDF posted to Canvas if you want to pull that open, make it a little bit easier on your eyes. But essentially, it's kind of got this row and column heading. Excuse me. The row headings tell you the first decimal, and then the column headings tell you the second. So we wanted negative 1.29, right? So we're going to say, okay, what's the probability I saw that Z-score of negative 1.29 or anything below it? I'll find negative 1.2. So it looks like it's right here. I then go over, what was my second decimal? 1.2, so 0.09. So negative 1.29. And the probability associated with seeing that Z value or anything less than that is 0.098. So that's how I'm going to use this Z table to find these probabilities. What if I had instead 1.29? Now I can use the table again, but I also want to use this to highlight something important about this. Yeah, remember to do it this time. The standard normal distribution. Right? If I just found that the probability or the area under that curve to the left of this Z-score of negative 1.29, if this area was 0.0985, that's what we found in the table. And then I said, well, what's the probability that you see something to the left of positive 1.29? Without using the table, how could I find that?
1 minus 0.0985.
Yeah, because if this is a symmetric distribution, what's the mean? We standardize it 0. So the area to the left of negative 1.29 will be the same as the area to the right of positive 1.29. So if this is 0.0985, what's the area under the curve? 1. So how do I find the area to the left of this value? Just 1 minus area to the right. Now I can look this up and prove this to myself. So I get what? 0.9015, if I'm doing math in my head correct here. Sure enough, if I go down here to 1.2, and the Z table will have like 2 pages. One will have the negative values, one has the positive values. So I go 1.29, that probability, sure enough, 0.9015. So I can look up positive Z values, I can look up negative Z values. Sometimes if I find one, like it gives me a little bit of information I could find, you know, what I kind of made the point. I don't necessarily have to then use the table again if I kind of think about what this would look like visually. And the fact that it is symmetric. Excuse me. What do I have here next? So I'm going to do something slightly off slides here. So if I had this, right, I now know kind of the different probabilities associated with this. So if I was looking at something between negative 1.29, 1.29, what's the probability that I see something within 1.29 standard deviations above and below the mean? Well, if I wanted the area in between these two, what's the area below negative 1.29? We said that was 0.0985. We could then go and look up 1.29 in the table. Okay, if the area to the left of this is 0.9015, what's the area to the right? Minus 0.9015. Right? So we're really exploiting the fact that the area under the curve is 1. Okay? So if I know the area to the left of any value, I automatically know the area to the right. Yeah.
0.015.
Oh, sorry, I'm right. Oh, yeah. No, I got this right. So remember, this 0.9015 is the entire area to the left.
Sorry, I was right.
So, yeah, this was, I didn't write it out yet. There we go. Does that clarify? Yeah. So 1 minus 0.9015 would be 0.09. So what's the area in between here? 1 minus what? 0.0985. Also minus 0.0985, right? So I'm getting what, roughly. What did I write wrong here? This is an 8. So this is going to be what? 0.8. Got what? 0.03. I'm doing math. No. Yeah, I'm doing math in my head correct there. Right. So I'm getting something very close to what? 80%. Right. So we'll see this benchmark kind of pop up. This is going to be close. If I'm looking 1.29 standard deviations above and below, that's roughly going to give me about a 80% chance of seeing something in that range. Okay. Now, obviously, like we're kind of stopping at the second decimal, so it's not exactly 80, but it's kind of getting as close as we can. And we'll see this pop up in, what do you think? Maybe a thing hopefully you've heard before. So if I want to know the probability that something's in between the same number of standard deviations above and below, do you guys ever talk about confidence intervals? That's where this kind of starts to come from. So, excuse me. So just different ways of kind of thinking about how we're going to use this Z table to find these different probabilities. So we already talked through this. We looked that up in the table. What if I had a question where I asked you to find the probability that Z is greater than or equal to negative 2.53? Well, what would you do? So now I want the probability it's greater than. So anytime you're looking at these, I would draw this out, right? So if I want the probability that it's greater than negative 2.53, here's my normal distribution. What I actually want is the area above that value. What does the table tell me? The table tells me the probability that I see this value or anything less. So the table gives me this area. So what am I going to have to do?
Positive.
Subtract that from 1, huh? I could look up the positive value as well. That's another way of getting at it, right? I could look up positive 2.53. If this is symmetric, that should be the same. Whichever way is easier for you to think about, you can do that. In fact, right now, we'll kind of show that we get the same value here. Okay? So I've actually got tables. I'll switch over in a second. I'm trying to get this pulled up for us. If I can. Oh. Rows. Okay, there we go. All right. So if I looked up negative 2.53, negative 2.53, the area to the left is 0.0057. Well, if that's the area to the left or less than that value, we wanted to probably see that value or greater, we would have to subtract that from 1. So we get what? 0.9943, right? Or to your point, if I looked up positive 2.53, the area below positive 2.53 should be the exact same thing as the area that's above negative 2.53. Sure enough, I get that value of 0.9943. So whichever way is easier for you to think about. I think some people, it's just easier to kind of look it up and then subtract it from 1 just to kind of, I don't know. It just depends on how your brain thinks. I find most students make fewer mistakes doing it that way. But the fact that it is symmetric, yeah, you can look at the positive value and then it's the reverse area, right? Table tells you the area to the left. If you want the area to the right and you make it positive instead of negative, that'll be the same value. All right. So what else do I have here? We got what? 35, so we got 15 minutes. All right, I'll show you this. So you could do, if I know the probability is of being greater than negative 2.53, what's the probability it's less than? Well, this is the value that I just directly got from the table. Right? Kind of nice and easy. So some common Z-scores we're going to see pop up, especially next class when we start talking about confidence intervals, is going to be this kind of set of values. Why? Well, notice what are these kind of close to? 90%, 95%, 97.5, 99, 90. These are going to be some kind of benchmark values that we see pop up a lot when we start talking about hypothesis testing and confidence intervals. Okay. So before we kind of keep moving, and I've got some examples here, we can use the inverse transformation. I want to stop and talk about sampling distributions. I want to make sure we have enough time. Now, this isn't for points, so this is not going to be, but I'm kind of using this as like a practice of when I use these in-class kind of quizzes, this is generally what they'll kind of look like, right? So I've talked about some material. I'll hit the publish button, have it set to be open for 5-10 minutes, depending on how long I want to give you to work on them in class. You'll see it pop up under whatever week we're at on Canvas. You'll kind of click on it. Yours will look a little bit different at this point, and it actually pull up the problems. You would see this if you click on the quiz. Once again, this isn't for any points today. I'm just kind of thinking about what this would look like. So we've talked about kind of Z tables, probabilities. I'm just trying to get a little more practice with them. Like I said, I have to go through a little bit quick, so we have time to kind of cover more of what I want to get through in this class. You should hopefully have that for this. But let's say I have the exam, the midterm for this course, and I think the mean was about a 78, and I had, let's say, a variance of 144. Okay. So I've got some of the things that I might need. What is the Z-score for a student that scores a 70? So this one we're going to kind of walk through together today. I just want to give you an example of the types of problems you would see after we covered stuff in class. So I've got the information that was given to me is that the mean of this test score was 78. The variance was 144. And I wanted to know the Z-score. No, I already forgot what it was. 70? All right, thank you. So I want to know for 70, what is my Z-score? Okay. Yeah. So I'm going to take this value. How do I calculate a Z-score? I take the value I'm interested in, I subtract the mean, and I divide by the standard deviation. So I have the variance. How do I find the standard deviation? Yeah, I just take the square root of the variance. This would then cancel. So the square root of 144, 12. So I'm going to set this up. I've got my test score of 70. I've got the mean on that test of 78. I'm then going to divide by that standard deviation of 12. And I get a Z-score of what? Approximately negative. I think that's right. 8 over 12. No, 3/4. No. 8 over 12 is 2/3. So 0.67 negative, right? Because I was below the mean. So right away, if I was asked this question and I look at that value and it's below the mean, I automatically should be thinking negative Z-score, negative Z-score, negative Z-score. The Z-score represents how many standard deviations away from the mean I am. If I'm below it, it should be negative. So here we've got negative 0.67. Now, if I had extended this question to say, what's the probability I see somebody scores 70 on the test or any lower, right? So we can work in either direction. So let's say I'm thinking about that test score. And I say, what's the probability that they score a 70 or anything below that? Well, I can turn that into this Z-score of negative 0.67. And now I can use the tables to find that probability. So what will I do? Go. I need a tab pulled open. So I'll go to my Z tables here. I'll look up negative 0.67. Pulling some time here. So negative 0.6, and then my 7 column is right here. So negative 0.67 looks like it's about 0.2514, right? Or there was about a 25% chance that someone scored a 70 or lower on this test. Okay. And I could do this for any value of X I was interested in, right? So here we were simply asked about what the Z-score was, so we had negative 0.67. But I could add a question there to find the probability then after we do that. Any questions on that before we? So this is going to lead us into next class. We're going to have to think, we really have all the tools we need, but we can also work in the opposite direction, or what we would call kind of the inverse, okay? So let's say instead I had a question where if I had the same mean and variance, what test score would put a student in the 90th percentile or the top 90% of the class? Like that, what's the cutoff to kind of be in that top 10%, right? If you're in the 90th percentile, it's like the cutoff for the top 10. So let's kind of think about what this looks like visually and think about how we might be able to solve this, okay? So what I'm looking for, well, I've got this standard normal, and then I've got my variable X test score I'm looking at. So I want to know, all right, there's this mean of 78, and we already said this standard deviation, we converted the variance to be 12. What test score is going to make it such that the probability of seeing that test score or anything below it 0.9, right? That would be the 90th percentile cutoff, okay? So I'm going to work in reverse now. I don't have the X value, but I have kind of been given the probability that I want. So if that probability is 0.9, how can I use those Z tables to then find that? Well, all these numbers in the middle represent the probability of seeing that Z value or anything below it. We know we want that probability to be 0.9. Now, right away, what should I be looking at the negative Z values here? What's the highest probability I should find from the negative Z values? If I had negative 0.000001, that probability is going to be very close to. So if this is a symmetric distribution, what's the probability I see 0 or below? 0.5. So all of these values should be less than 0.5. Sure enough, as I get close to, at 0, it's exactly 0.5. So 0.00, the probability that you see that or anything below it is 0.5. So I know I need to go a positive or have a positive number of standard deviations above the mean, or my Z value is going to be positive. So I start looking here, where is 0.9? Now this is where I can't get exactly there, but I can get close, right? So typically when we start to have questions where we're doing this reverse procedure, the inverse, you'll find the probability that's as close as you possibly can get. And then you would take, if you're in between two, you'll take the higher of the two. So in this example, I've got 0.8997 or 0.9015. I'll take the higher of the two. Now, what that always is going to do is put you slightly above that. So it's actually going to kind of like err on the side of caution. I'm not quite at the 90th percentile here. I'm actually at like the 90, 0.15, 90.15%, but we're getting as close as we can. So here I go. What Z value would that be? 1.29. Sure enough, it's one of the values I said will start popping up a lot because it's going to be associated with kind of that 90th percentile cutoff. So we know that the Z value that is associated with a probability of 0.9 is 1.29. So we just found the Z value. Now at this point, you could just take your Z value equation and start plugging things in. We had 1.29 was the Z value that gave us that desired probability of 0.9. We don't know X, we know the mean, and we know the standard deviation. Now it's just a little bit of algebra to solve for what X is, right? Now, if I rearrange this equation, so I multiply both sides by the standard deviation, I add the mean to both sides, we're going to end up with an inverse kind of transformation formula. Now, you can always start out here, plug it in, and then do the algebra. Or you know that when we're using the inverse method, we can always use this inverse transformation formula, because when you rearrange it, that's what it would always be. So if we do that, we can just plug in 1.29 here, 12 here, 78 here. I don't know what this is off the top of my head. I'd have to actually break out a calculator if anybody wants to help me. But it looks like it's going to be what, roughly 12 times 4. Thank you. 93.48, right? So in order to get into that 90th percentile for that 371 midterm, I need to be scoring about a 93. It's a very weird example. Shows a variance that isn't the actual variance for the midterm in this class, and the variance is really high, and so that's why we kind of end up with this 90th percentile cutoff being a little bit higher. Okay. Any questions? Is this looking? Hopefully, you've seen this before. I'm getting some head nods. Okay, so we're going to be using these Z tables to find these different probabilities. Next class, we're going to kind of train talking about hypothesis testing and then confidence intervals. So a lot of classes, they do it in the reverse order. They talk about confidence intervals and then hypothesis testing. I think that based off what we've talked about, it makes a little more sense to do the reverse. So that's kind of the order in which we'll do it. We'll also take a look at how we do some of this in Stata. So today we didn't get a lot of work. We didn't get any work in Stata, but I want to mention a couple of things before I let you go about Stata as you're working on those problem sets before we get out of here. So we're done with content here today. However, there was some things I failed to mention last class that'll help you as you work on that problem set a lot. So I would listen. So when we have Stata open, nothing that I type, nothing I see here gets saved anywhere. Okay? The only thing that gets saved is whatever I type in this do file, which we said we can open up using that notepad tab. Right? So I've got my do file opened up. And I also have the program over here, which will run all of my commands. So if I go to file open, right, and I use that review of statistics file that we were looking at last class, now I can only open up files from my OneDrive. Can't open them up from your downloads folder on your device. It has to be from your OneDrive. So you're gonna have to drag and drop those files. I know I said this last week, but you have to drag and drop those onto your OneDrive. Once I open up that do file, I kind of probably didn't elaborate enough as to why I do this step here. So I said that initially you can go to like file open or file import that data, but it's really handy to kind of save what that file path is, because my file path is going to be different than yours. Depends on what folders I'm putting in. However, if you change the file path right here, so this is the do file that's on Canvas. If you change the file path to yours, I always write the code so that everything after that will use your file path. So you can run all of this code. All you have to do is kind of set the path to be whatever your file path is, whatever folder you're putting these files in. So I'm going to do that here on this device, right? My personal computer, this file path is different. I just copy and paste it in and I can still run this do file. So I've opened up this data that we looked at last class, but now like all this code, whenever I run all of this, none of this is getting saved. All this output is just temporary. You can't save it anywhere. There's no file extension you can say. All you can do is you have the data file, the data that you're using, and then all of the lines of code, the commands that you want to manipulate that data with, those commands, that's what you're saving. It's essentially, you can think of it as like a Word document, but it's a usable Word document. I can then open it, highlight it all, hit that execute button, and now it runs all that code very quickly again, leaving off wherever I was at before. Okay, so I would try to, when you're looking at the do files we use in class, have your file path, like, I don't know, copy it, like the folder that you're putting everything in, copy and paste it somewhere in a Word document that you could just very quickly in class, like copy and paste it into the do file. You don't have to do it in class, you do it ahead of time, right? But copy and paste your file path into that global command. And now you can just open up, if we use multiple data files in the same class, you can just run all the code and it'll just kind of keep using your specific file path. So that's a little bit more important than I probably gave it credit for, is starting to get used to this syntax of creating or generating your own file path here. And then I write all the code so that it'll just use your specific one. So we'll use that quite a bit next class. So I've got kind of where we left off. I'll probably revisit the standardization stuff. Then we'll kind of jump into week 2 Stata stuff on Thursday. And we'll also start to then look at hypothesis testing confidence intervals. Okay. So like I said, try to start working with that first problem set early so we can get those easy questions out of the way. And then I'll hopefully finish everything up on Thursday for the remainder. Okay. All right. We'll see you guys on Thursday.
That.